In this section, we'll be taking a look at the BGP signaled Layer 2 VPN concept subjective of the JNCIP SP exam. We'll cover the control plane and the data plane. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V, and JL3V.
In this video, we're going to take a look at BGP signaled Layer 2 VPNs. And these Layer 2 VPNs provide point-to-point virtual circuits between customer endpoints. In the example on the board, we will be providing a point-to-point virtual circuit between CE1 and CE2. And BGP signaled Layer 2 VPNs have much in common with BGP signaled Layer 3 VPNs. And we'll walk through some of the similarities and differences in the signaling architecture in this video. So we have an example network outlined on the board. So we have our CE devices interconnected to our PEs, which are interconnected via the Ps in the middle. And much like with Layer 3 VPNs, we have LDP or RSVP running in the core of our network that's providing label switch paths between our PE routers. And these label switch paths are carrying the traffic between our PE routers. We're using the outer transport label to switch traffic along these label switch paths from PE via P node to PE. And this is the same in Layer 2 VPNs and Layer 3 VPNs when we're looking at BGP signaling. We also have multi-protocol BGP running between our PE devices, or maybe via an intermediate route reflector. And again, much like Layer 3 VPNs, this is providing the signaling of the virtual assets that we're providing to the customer. In the case of Layer 2 VPNs, it's providing the signaling that's facilitating the establishment of our virtual circuits, of our point-to-point links. And because we're providing signaling for these point-to-point links, compared to a Layer 3 environment where we're providing signaling for routing, the information that we're carrying in multi-protocol BGP is going to be different. And let's analyze what L2VPN signaling looks like now from the purpose of multi-protocol BGP. So we have a different address family indicator and subsequent address family indicator. We're using 25 for AFI and 65 for SAFI. And the NLRI, the network layer reachability information, is outlined here. And let's walk through some of the fields that we find in this NLRI. So we have the length indicator at the start. We then have route distinguisher. Route distinguisher is providing exactly the same functionality as we have with Layer 3 VPNs. It's making the identifiers that we have contained within it unique to a given private network. This means that we can support many different customers, and we can provide these many different customers with many virtual circuits. Much like with Layer 3 VPNs, we can support many different private networks, each dedicated to a customer, accommodating overlapping address spacing, that sort of thing. Then we have our CEID. So this number is going to be identifying an endpoint and is going to be unique within a given VPN. And then we have three values that relate to the MPLS label that we're going to be pushing onto a packet on transmission and removing of a packet on receipt on ingress and egress PEs. This is the innermost label we're talking about when we have a multiple label stack when we're going through this MPLS signal network. Remember, LDP and RSVP will be signaling the outer label, and these are referring to the inner label. And we'll discuss how these values are used to generate that transmit and receive label in a later video. And then finally, we have additional optional TLVs, additional optional type length values, and we can encode additional information here. The main one that you need to be aware of is the circuit status vector. Now this is a bit vector that will be advertised by PEs, and each bit position in this bit vector is going to indicate the health of particular virtual circuits that relate to CE endpoints. If we have a value of 1 in a given position, that means that the CE that refers to is down, or the virtual circuit to that CE is down. And this is how we can provide monitoring information between an ingress and egress PE, so we can track the operational status of virtual circuits on a given PE. So this is the NLRI that we are advertising in multi-protocol BGP. Along with this NLRI, we are also carrying 2 additional extended communities. The first is the Layer 2 Information Extended Community, and this is going to be referring to things like the encapsulation that we have between the CE and the PE. You know, is this an Ethernet virtual circuit? Is this an ATM virtual circuit? Are we using VLANs? That sort of thing. And it's also going to be telling us the MTU of the circuit. So we can be using this to ensure that there are no MTU mismatches end to end on that virtual circuit, so that we're not going to be causing any strange issues when that circuit comes up. And we're carrying additional control information as well. And then finally, the second extended community that we're carrying is root target. And again, much like layer 3 VPNs, it's performing exactly the same function. We're going to use it to control what endpoints are allowed to be able to form virtual circuits to each other by virtue of those endpoints being imported into a given VRF or not. And in this video, we took a look at the BGP layer 2 VPN control plane. In the next video, we'll take a look at the data plane. In this video, we're going to take a look at the data plane of BGP signaled layer 2 VPNs. So with BGP signaled layer 2 VPNs, we can support a number of different encapsulation types of the virtual circuits that we are providing to our customers. We can support Ethernet and Ethernet VLAN virtual circuits. We can support ATM, frame relay, PPP, and HDLC. And to the customer, when we provide these virtual circuits, they appear exactly as if they were a native Ethernet circuit, a native ATM circuit, etc. By far the most common encapsulation technique in use today is obviously Ethernet, but just be aware that those others are available. So we have all this signaling in place in our network to establish virtual circuits. In this case, a virtual circuit between CE1 and CE2. So what does the actual data plane packet look like when PE1 comes to send that packet into the MPLS portion of his network for onward switching to eventually get to PE2 to then be forwarded onto CE2? So this is the packet that I've illustrated here. It's an Ethernet virtual circuit, so we have the encapsulated frame, and above the frame in the stack we have an optional control word. So the control word is part of this virtual circuit encapsulation process. It's mandatory when the encapsulation of the virtual circuit is, say, ATM or frame relay. And it's mandatory in these cases because it's there to provide strict sequencing of those packets, strict ordering of those packets, because that's important in the encapsulation technique that we're emulating. For Ethernet virtual circuits, the control word is optional. However, it is still useful in some cases for Ethernet virtual circuits. An example would be if we had equal cost multipath going on in our downstream MPLS network. So we had lots of parallel links, maybe across LACP bundles or maybe you're just routing between multiple PEs and Ps. In this case, the control word helps to identify the traffic correctly on the downstream devices, so that we will hash the traffic appropriately onto one of those multiple parallel links, i.e. we keep all traffic belonging to one virtual circuit on the same parallel link. If we weren't to do that, if traffic was misidentified and it was sprayed across multiple parallel links, then this could lead to reordering on the egress PE. And obviously this can cause issues with certain types of traffic flows. So that's the control word. Next up in the stack, we have the label that's identifying the virtual circuit endpoint. So in this case, we'd be identifying C2 here. And then above that, we have the label that's the start of the LSP that's going to get us to the PE device where this virtual circuit terminates. So how are we generating this inner label, the label that identifies the virtual circuit? So there is this process that we have illustrated here on the left-hand side of the board that's carried out both for transmit and receive of this inner label value. So as I've mentioned, we are advertising this NLRI from P1 to P2 and vice versa from P2 to P1. And the CEID and these label block values, all contained within the NLRI, are used by the PEs to calculate the label to apply to a packet for transmission, and also to calculate the label that should be received when that packet has been received from the MPLS core for transmission onto the CE. And so these are the rules that are used to calculate that data plane state. So if we're looking at PE1 sending this packet to PE2, that is the transmit label that we're calculating. We take the remote base, so that's the label base that we've received in the NLRI from PE2. We add to it our local ID. So that's the ID that's been generated that indicates the link to the CE. And then we take away from this the remote offset. So the offset value, again, that we've received in the NLRI. And then we do this process again for the receiving label, so the label that we're going to be expecting on packets sent from PE2 to PE1. And all of these values are effectively inversed. We take the reverse options. So in this case, we have the local base. So that is the label base that we've allocated. We're taking the remote ID. So that's the CE ID that we've received in the NLRI advertisement from PE2. And we take away from that our local calculated offset. And that's how we generate the receiving label state on the PE. We would obviously, of course, follow this same process on PE2 as well. And in this video, we looked at the data plane of BGP signaled layer 2 VPNs.